Hello again. So here's what we're going to do for the last one. For the last video we have for this week, what we'll do is we've seen, in the first video, we saw how MATLAB can time itself basically on computations. And in the second video, we saw how to solve a given linear system in 3 different ways and how to express that in MATLAB, right? If I scroll up, here's what we did in the last video, defining these variables, and we saw that each of these there are 3 different ways to solve the same system, and it gave us the same answer, right? But again, MATLAB is always going to provide round-off error when the numbers aren't so quote-unquote nice. And when that's the case, we want to compare the difference. We want to talk about error of an approximation, right? Each approximation will have its own error, or each method, excuse me, each method will have its own error. And we want to be able to quantify that and then compare, which round-off error is worse, which one's better. And then we can also compare the time it takes to compute using each method. And then we can compare that. And then what the end of the lab will be is you guys answering some questions about what can we conclude from everything we've done. And so I want to first just run this section and see what happens. So if we run this comparing the methods section, we get this table down at the bottom here. So the first column is the method, right? You can use reduced row echelon form. You can use the inverse of A or the backslash operator. And in the second column, each entry will tell you the time it took to compute the solution using that method. And so in the code that's given from the M file we downloaded, all of this, you don't have to worry too much about what's going on here. But what it does is it's computing the time and the error. And there's 2 kinds of errors here, right? And first, let's note that you can see the inverse and the backslash operators have not yet been implemented. And that's because we haven't defined them. In the M file you download, we only have solving with reduced row echelon form, right? We'll want to do something similar with the inverse and the backslash operator. But for now, let's talk about the reduced row echelon form, the first row in this table, and let's see what's happening here. So there's this error, and then there's this residual error. And I want to talk about what these things mean. So this column here, error, we can also call this the solution error. So solution error. So what this means is if we know, let's say we have a system, again, AX equals B. And let's say we know the true solution, right? No round off, no approximation. We know the precise solution. So we'll call this X sub T for true solution, okay? True solution. Okay, and then let's say using MATLAB, we compute, for a given method, we compute this approximated solution, right? Taking these round off errors. It's cutting off these decimals at some finite length, right? So this will be the approximated solution, or the, whatever MATLAB computes, approximated solution. So the solution error down here is defined to be equal to X sub T minus X sub A, okay? And remember, this is going to be a vector, right? This solution error will be a vector because the true solution and the approximate solution are both vectors, right? Difference of 2 vectors is a vector, okay? And then there's this residual error, and we can talk about what this is. Residual error is slightly different, right? You know, the reason we're doing this is because we want to take a system that we don't know the solution to, and then we want to calculate the solution, right? And so if we don't know the solution beforehand, it doesn't really make sense to compare with a true solution if we don't even know what that is, right? And so this residual error is a way of computing error that accounts for that. It computes error without actually knowing what the true solution is, which is pretty cool. And here's how residual error is defined. Take R, we'll define this vector R. We're going to define it to be A times our approximated solution, right? Or whatever MATLAB calculates, A times XA minus B. This, again, is also a vector, right? This is our residual error here, right? And so, you know, the closer XA is to XT, right? We just don't know what X sub T is in this case, right? But if we had that XA equals XT, well, then that would mean that the residual error is 0, right? Because if we have A xt equals B, well, then A xt minus B is going to be 0. So if our approximate solution is the true solution, then we'll get a residual error of 0. So that means the closer x sub A is to x sub t, the smaller value we'll get for residual error. And like here, that's pretty good, right? 3.44 times 10 to the negative 15th is a pretty good approximation, right? That's a very small difference. And so now what we want to do is we want to calculate this for the other methods. We want to calculate this for the inverse, and we want to calculate this for the backslash operator. And let's see how we can do that. First, to see how we can do that, let's understand the code that's written for reduced row echelon form. So let me clear all this here. It's not so cluttered. We want to solve with reduced row echelon form. So I'm looking right up here. And kind of the bit of code that we're going to use is to compute the time it takes, right, which we are going to compute the time in each case. We'll start this little block of code with tick, right? That starts counting. That starts a clock for MATLAB to time itself, basically. We'll define everything we need, right? We defined a reduced row echelon form, matrix of the augmented matrix A and B. We called it S, right? And then we define the solution, X sub RREF, to be just the last column, right? If A is an n by n matrix here, so A is an n by n matrix, B is a 1 by n vector, that means our solutions are also going to be 1 by n vectors, right? And so this X sub RREF is the reduced row echelon form. We want all rows last column, right? So it gives us the last column. And then we finish this with a variable called RREF underscore time, and we just define it to be talk. And if you write talk, it stops counting. It stops the timer you started up at the top there, and it records it in the table. And what we want to do, right, we see these are not yet implemented for inverse and backslash. We want to write a little block of code for each one to complete this table. So let's do that. So maybe I can start, whoops. Maybe I can start a section here. Let's say solve with inverse. Okay, and I want to start timing. So we'll go tick. I want to then define my solution, right? X inverse, what do I want to be? I want it to be the inverse of our matrix A, which remember, what is A? Well, where am I? Oh, so by the way, something I should have mentioned, when we're doing this comparing the methods, we are taking A to be a 200 by 200 matrix. Okay, but in general, I mean, we can do this for an arbitrary n, but just for what we're calculating here, we're looking at n equals 200, right? We're looking at the system AX equals B. Okay, and so what that means is X inverse is going to be inverse A times B, right? And then what else do we want? We want, so we don't need that output. Then we also want inverse calculation sub time. We want to see how long it took. So talk. Okay. So that's all we need for the inverse. And let's hit run section. And if we hit run section, look, you can see we get a calculation for inverse. We get a time calculation, a solution error calculation, and a residual error calculation, which is what we're after, right? And so let's compare these two, right? If you compare the error versus the time, what do you see, right? And it gives you kind of a gauge of when to use what. If you're looking for something that computes much faster, but gives you less accurate results, right? Maybe you don't need to be as accurate in a given application. Then you might think, if you're comparing reduced row echelon form versus inverse, you might say, okay, well, maybe I should use the inverse in this case, because I don't need as accurate results, and time is more of the essence in this application. Whereas if you were looking at something where you want to be very precise and it doesn't matter how long it takes to run, then, you know, comparing these two, you might say, all right, well, maybe I should use reduced row echelon form method. And lastly, we can do this again for our third method here. So let's solve with the backslash. Okay, so what do we get here? Let's time this, tick. And then I want X sub div, I'll call it. And I want this to be A slash B, right? I want this to be the solution corresponding to the backslash method, right? And then again, I want to time this. So time sub div, and we'll say talk. And we can hit run section. Okay. So made a small error there with naming variable, got the names flipped. So if I name that variable correctly and hit run section, there we go, there's no problem. And now you can get a comparison for all three methods. And so to wrap this lab up, what you'll do is you'll answer some questions about what you're observing and what methods are considered quote unquote best. You want to kind of answer some questions about comparing these methods. And so this pretty much wraps up the fifth lab. And it's pretty cool because we learn a lot about how MATLAB can time itself to tell us how long its computations are taking. And when it can do that, we can learn when to adapt certain methods based on our applications. And so this will help us get a better understanding of when we should use which methods when we apply MATLAB in the future. So I will see you guys next time.